Hello and welcome back to the fourth session in our extended reality lecture series, where we will cover the topic of graphics rendering pipeline and geometry within it. So at the end of our last session, we took a look at the principles that are found in the majority of photorealistic depiction literature, which are the geometry, materials, lighting and camera, post-production, and the rendering engine. When we are talking about the rendering engine, we could take a look at the earlier days where we took a look at the bucket rendering, which used the CPU and its many threads and cores. So moving away from the bucket type of rendering, we were introduced to the progressive rendering type, where we can use the CPU but achieve much better results by using a GPU. In modern days, we have an XPU, which is an adaptive thing which can accommodate itself to the tasks at hand, like we see in this example from RenderMan. However, when we are talking about interactive visualizations or visualizations within VR or any other extended reality apps, we have to consider that these images need to be created in a very short amount of time. So when we are looking at this structure, it needs to become more complex. It needs to have another dimension added to it, and that dimension is seen as time. So when talking about creating visual representations in VR or any part of the extended reality, we have to discuss the real-time rendering of it. This book provides excellent guidelines to real-time rendering. So within this book, we have the definition that the real-time rendering is concerned with rapidly making images on the computer, and the rate at which images are displayed is measured in frames per second or hertz. So we have frames per second or hertz, which is basically a frequency, but in this case, we need to discuss something that is called critical flicker fusion frequency. So critical flicker fusion frequency can be defined as the frequency at which flickering light can be perceived as continuous. So if we take a look at a blinking light, which is blinking at a certain rate, so a certain frequency, around 60 hertz is something that a human can still discern if it's blinking or not. Above that, it just seems like it's continuously blinking. But we have different ways of perceiving our reality in reference to our metabolism within the animal kingdom. So for example, for a leatherback sea turtle, it observes reality with 15 frames per second, while cats are similar to humans with 55 frames per second. Dogs are determined to observe reality with 80 frames per second, which is when we can introduce this concept of when you have slow processing, the time feels fast, and when you have fast processing, the time seems slow. It's similar to turning on the slow motion video on your phone and recording a video where you are actually getting 5 to 10 times more frames than you would have with regular videos, which means that the time passes slower in this case. So the higher frame rate, the slower the processing time, and vice versa. This is why when we, for example, take a look at the housefly, which has a very fast metabolism and around 250 frames per second for observing reality, that's why it's very difficult to catch a fly with your bare hand. It's because you are moving so slowly in reference to the capabilities of the fly to detect movement around her. For example, if you wanted to catch a fly and you were moving your hand very slowly, it's like growing grass for us, if we want to make an analogy. So once we are familiar with this frames per second and the critical flicker fusion frequency, we can introduce the graphics rendering pipeline, whose main function is to generate or render a two-dimensional image given a virtual camera, three-dimensional objects, light sources, and more. So think of graphics rendering pipeline as this assembly conveyor belt in a factory. So you have to do one thing before you can start doing the other. Some things can be done in parallel, but in order to just dumb it down, in order to understand the concept, we will take a look at it like this. So in the book, The Real-Time Rendering, it is depicted like this, where you have the application, which is basically the software you are using. And it says, as the name implies, the application stage is driven by the application and is therefore typically implemented in software running on general purpose CPU. So the CPU is basically like a huge pipe which can take any task and then produce the output in reference to what is needed. So it's multi-purpose and it can do any type of work. On the other hand, when we take a look at geometry processing, for example, which is the next main stage, it deals with transforms, projections, and all other types of geometry handling. The geometry stage is typically performed on a graphics processing unit or the GPU. Then we have the rasterization stage, which typically takes as input 3 vertices, forming a triangle, and finds all pixels that are considered inside that triangle, and then forwards these to the next stage. And the next stage is pixel processing, which executes a program per pixel to determine its color. So the rasterization and pixel processing stages are also processed entirely on the GPU. So in order to understand this concept of GPU being implemented within the graphics rendering pipeline, we can take a look at the Book of Shaders explanation, which is something like this. So you have the CPU, which is, as we said, a huge pipe which can take any amount of tasks, but it has to take it one step at a time. And it can do any task, but it has to be one step at a time. But when you have, for example, 1,000 by 1,000 pixels that need to be rendered, that's 1,000,000 tasks that need to be done within a second or even less, which is why it's important to introduce the GPU, which as a concept is introduced as multiple little pipes that only do one task that it's given. So it cannot do a lot of other tasks. It can just do one program. For example, add a color to each pixel without considering what all the other pipes are doing. So when we understand how the graphics rendering pipeline works, we can take a look at computer graphics, principles and practice, where it's depicted like this, or the GPU-based interactive visualization techniques, which depicts it like this. However, regardless of the principles, we have the primitive assembly or the geometric transformations or the geometry processing as the first part, which coincides with the first principle that we use for the photorealistic depiction, which is the geometry. So now that we know that geometry is an essential part for the start of photorealistic depiction process and also the graphics rendering pipeline, we can take a look at it in more detail and just use all the principles that were in reference to geometries but were not defined as objectively as needed. So as an example, we can use a wine glass or an image of a wine glass to construct or draw the profile curve and then just use rotational surfaces or lathe modifiers to create the mesh, which adequately depicts the real life. In this case, we are talking about proper proportions, which means that we can create something that depicts real life objects. However, by distorting these proportions a little bit, we can create whimsical depictions, which is basically where the subjective part and the objective part diverge so that you do not create the atmosphere or deliver a message with objective things, but you completely go to a non-photorealistic rendering or stylized version. Afterwards, we can talk about object material depth, which is closely related to materials. So for example, if we take a look at this, this is basically a curtain or a protection while the facade is being reconstructed. And it looks like the normal map or the bump map was not added. So in the 3D photorealism toolkit by Fleming, the object material depth kind of has a transition property since it can be both geometry and materials. Another important principle for the geometry part are the beveled edges, which is something that was seen in most of the literature review we did in the previous session. So when you have beveled edges, regardless whether it's a photorealistic depiction or a stylized one, the lighting and the shadows, as well as the highlights, are something you're accustomed to as opposed to the harsh edges that exist, for example, on the left image of this crate or box. Now, as we can see, these four principles are very low or connected to the base of this pillar here, where using a reference is a major part, while the proportions and object material depth and beveled edges contribute, but not in a large amount or not as significantly as the next principle, which is the chaos part. So chaos and clutter is the first principle that was viewed in the first book we took a look at, the 3D Photorealism Toolkit, where it says that chaos doesn't mean that everything is completely disorganized, but it does mean that no two elements are the same. It also means that everything in the scene cannot be aligned perfectly. This is very important, for example, when depicting interior scenes where you can just scale up or fluff up the pillows or put some articles on the table that resemble humans actually living there. And that creates a sense of imperfections, which is something that we are accustomed to, which creates more of a connection with humans. So that's the objective and the subjective part that we talked about in the last session, put to the test in this case. These 5 principles need to be observed in reference to the graphics rendering pipeline, where they say that we will focus on providing methods to increase speed and improve image quality, which is why we have to think about optimization, but not as something that is introduced last. So optimization is an important aspect of real-time rendering, but when talking about geometry, it mostly comes down to the level of detail. So the level of detail can be considered through these 3 aspects: overall shape, light interaction, and curvature. So we can take a look at this example, which was part of the lecture Low Poly Modeling at the GDC, where we can see a hand which only has 800 polygons and a hand that has 3.4 thousand polygons. Their overall shape is similar, and it's also functional to be used because it can bend in different directions. The hand on the utmost right has a larger amount of polygons, which is why it can have a better curvature, but then it comes to it whether we would like a photorealistic depiction of something or a stylized version of something, or a low poly version in this case. Also, in both cases, we can see how the light reacts or how the shadows intertwine with the geometry, so we can create the atmosphere or the feel for the geometry or for a certain space just with a lower amount of polygons. When we take a look at the other hand depictions, we can see that they are not the same, but are dumbed down, or the polygon count is reduced in reference to what needs to happen. So if we only have one articulation of the finger, or the entire articulation of this part of the hand, or just something that is supposed to interact as a fist. So we are dumbing down in reference to the function we can use. Other examples use the decimate function, which basically means that we are reducing the polygon count, but we are also reducing the functionality as well. So in this case, we can take a look and see that the 400, 256, 172, and so on type of meshes are not able to be used, or are unusable when we compare it to the 800 polygon count that we can see here. So once we understand the importance of the level of details and how to actually make functional geometries, we can introduce the concept of low poly, which basically means creating geometries with a lower amount of polygons, where it's very easy to create different variations and then improve on those later. So both scenes here have the same amount of polygons. However, they have different ways of generating the scene. The one on the left uses similar shapes and sizes to populate the entire geometry, so wherever you look, you can actually see something. However, the accumulation type scene has only specific focus points, which are more intricate as opposed to the ones that look the same. So the low poly approach has different applications in reference to what is needed in the end. So the low poly can be used to create high poly versions, but that can also be done by using adequate materials, which can be photorealistic or stylized. And that is a topic that we will explore in our next session. I thank you for your time, and I'll see you in the next session. Bye.